In last chapter, we discussed the distribution of a single variable. Now, in this chapter, we are going to discuss the relationships between pairs of variables. So that means at least we have one pair of data. When we look at this data, we need to ask if both variables are quantitative. If yes, then we are going to use a scatter plot for graphical display. So that's the first topic we are going to discuss, scatter plot. If both variables are associated, then we can calculate the correlation. We need to know if they are correlated and the correlation coefficient. We are going to discuss this. So this is the second topic. Sometimes we need to know more relationship between the two sets of data. For example, predict one set from the other. In that case, we are going to use mathematical modeling, and we can use a regression technique. Specifically in this class, we are going to discuss least square regression to fit the data and use the regression line to predict the data. If both variables are categorical, then we can use a to-be table to analyze them. So today we are first discuss the scatter plot. Most statistical studies involves more than one variable, so this we need to move from chapter 1 to chapter 2. When we discuss this data, we ask questions. First one, what cases do the data describe? That is a very simple question, it looks like. The second is what variables are present and how are they measured? The third one is are all of the variables quantitative? These three questions looks like relatively simple. And the last one, the next question is, do some of the variables explain or even cause changes in the other variable? This one looks easy too, but actually this one is very difficult for some situations. For example, the scientists are looking for, they want to find something, the function, the mechanism of cancer. They may claim that some mutation in genetic mutation will cause some kind of cancer. So they need to find if the change of one variable will cause the changes in the other variables. Definitely this is not easy, right? So, but in our class, we are going to discuss, we start from simple questions. We do not discuss that complicated questions. If you have interest, you can definitely study at a later time, at a higher level class. If we are presented with a pair of data, and we're looking for a relationship between them, we can follow some steps. The first one is we start with a graph. If we are given a set of data, like here, and we can draw this with a graph. The graphs we discussed before include, for example, bar graph, histogram, stem plot, time plot. All those are for single variable. And today we are going to discuss the new scatter plot. Right? And once we get all this, we are looking for the overall pattern and the deviation from the pattern. We can use the numerical descriptions of the data. For example, the mean, the standard deviation, and also the overall pattern, so the symmetric or left or right-sided skew. And here is the example. We are given two quantitative variables for each of the 16 students. The students are indexed as number 1, 2, 3, 4, all the way up to 16. And the first quantity is the beers they drink. The second quantity is the measured blood alcohol level, blood alcohol content. For example, for the student number 1, he drank 5 beers and his blood alcohol level is 0.1. I don't know the unit, but that is not important. So we only discuss the data. And the second one, adjunct 2, and the blood alcohol level is 0.03, and so on. We have all the data for the 16 students. We are interested in, is there any relationship between the two variables? That means if you drink more beers, will your blood alcohol level be higher? Right? How this will change? As we said, if we given this set of data, the first step is we draw the plot. Okay, now for student 1, in this plot, scatter plot, the horizontal is the variable for the number of beers, and the vertical is the blood alcohol contents. The unit is milligram per milliliter. And how we draw this? Okay, for student 1, the beers equals 5, so we look for 1, 2, 3, 4, 5 here. And the blood alcohol level is 0.1. So 0.1 is somewhere around here. So that is the dot. That is the point for student 1. Okay? So this one is for student 1. Then for student 2, the number of beers is 2, so here, and the alcohol level, blood alcohol level is 0.3. So this is 2. So this is 1, 2, and for 3. It's 9, 9 is here, and the level is 0.19, it is here. So we draw all this from 1 to all the way to 16. So, once we draw all this, we have the scatter plot. So once we get the scatter plot, we need to examine some questions. We look at the relationship by examining the form, the direction, and the strength of the association. The first one is the form. The form means, but look at all this dot. If they are linear, linear means they form almost a straight line. Or if they are curved, for example, if they are like this, or clustered means group by group. Or no pattern, that means totally random. So just randomly distributed around the plane. So that's the first one, it's called form. The second one is the direction. The direction usually means if the form is linear. So for example, this is a straight line. We assume this is linear, means straight line. Then this straight line can be positive, means the slope is positive, means it's increasing with the x-axis increases. This is positive. Or can be negative. Positive, so positive looks like positive will be look like this. This is positive. And for negative, negative will be like this. This is negative slope. For the next one is no direction. No direction can be arbitrary. For example, if all these dots are randomly, like in something like a circle or something, that's no relationship. Another one is special. If all the dots are horizontal, close to horizontal, that means this is still a straight line, but we do not call this linear. Instead, we call this no pattern. So if the dots look like this, then there will be no direction. Or all the dots will be negative, or the vertical, so also no direction. That means no pattern. The strength, again, if we know the form, in this case maybe a linear, like this, we need to look at if all the points are on the straight line. or on the curve or any, no matter what the form is. So in this case, looks like not all the forms, all the points are on the curve. Actually, some are very far away from the line. So we say this strength is weak. Right? If the dots are very closely or even perfectly on the line, then we call the strength is very strong. Can be as strong as, for example, 1. Right? Once we have this scatter plot, we also can check if there are any outliers. Outliers is defined as deviations from that pattern. So in this pattern, scatter plot, we can see this one may be an outlier. The form of an association. The first one is linear. We can see here, the form looks like go this way, and this one is look like this way. So it looks like a more straight line. So we call this one as linear. As we said, this one here, if you draw the line, looks like it must be like this. We can still draw a line, like horizontal. But we said that we are claiming there's no relationship between these two sets of data. The reason is even the line is straight, that means no matter how the x changes, increase or decrease, this value here does not change at all. So that means there's no relationship. And for this, the curve can be like this. So this is nonlinear, and it looks like this is exponential. So this is xp. And this one here, the fitted line may look like this. So it looks like this is the second order polynomial. But anyway, no matter it's exponential or even logarithmic, if you go this way, it's called a logarithmic. Or this second order polynomial, third order polynomial, or even high order polynomials, all these are called nonlinear association. And this one, that dots are totally randomly distributed on the plane. So we cannot draw no matter straight line or curve, so totally no relationship. So this. If the relationship, if the form is linear, this one or this, then we are going to have several. We are going to have, as we said, we are going to have positive or negative direction. So in this one is very, it's very good. So this is positive linear. Positive is because of the slope is positive. Let's recall the slope. The definition of the slope is, we know this is a horizontal line, and there's an angle here. So the slope, somebody use k or somebody use m, that doesn't matter. It's defined by the tangent of this angle. If this angle equals 45 degrees, then this tangent of 45 degrees equals 1. Anyway, if this angle is between 0, horizontal, or to 90 degrees, this one is always greater than 0. So that is called a positive relationship. Instead, if the line goes like this, that means with the increase of x, the y decreases. Then this slope will be k or m. Also, again, it's tangent theta. This theta will be equals this angle here. So we can see this angle, big angle, or you can use this small. This is negative. This one is angle is between from 90 degrees to 180 degrees. But anyway, this slope will be less than 0, will be negative. So this is called negative linear relationship. For this example, as we already mentioned, there's no relationship at all. The reason is you may say, okay, the slope equals tangent of theta equals tangent 0 equals 0. But physically, you can see these values does not change with respect of x. No matter how x changes from 2, 4, 6, 8, this one is keep constant 5. So there's no relationship between these two sets of data. And this one here looks like also random, right? And so we call this one no relationship. The next one is the strength of association. The strength of the relationship between the two variables can be seen by how much variation, or called scatter, there is around the main form. In this example, we know this is linear, right? So the line is like this, and we know this is positive, right? Because the slope is positive, and all the point, all the quantity, all the pair of data are on the line. So this is called a strong association. And instead of here, this one, the form looks like also linear. It's also like this, and also is positive. So this is also linear, also positive. But compared to this, this association is not that strong. So actually, it's a weak association because not all the points are on the line. So actually, this one is even very far away from the line. So this looks like a very weak association. Once we are given the scatter plot, we can discuss some details about outliers. Right? Outliers, we know what outliers is in the first chapter, but the definition for outliers here may be a little bit different than that in the first chapter. In the first chapter, we deal with only one set of data. If a data is very far away from the others, that is called outlier, but this is only in one dimensional. In here, that definition may not be very accurate. But anyway, look at an example here. Suppose we have data like this, and this point, this point, this point, this point, this point, and we have another point here. And the form of the relationship again is a straight line here, and is again positive. The association is very strong, right? So all the points are on the straight line. Now the question is this one outlier? If in the chapter 1, if we look at only the horizontal data set, this one equals 1, this equals 2, this one equals 3, 4, 5, 6. Looks like if you look on here, so this one is here, this one is here, 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 and here. But this data is here. So if we look in chapter 1, we look at only this data set, this one is an outlier. Again, if you look at the vertical data set, this value is here, this value is here, this one here, 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 and this value is here. So again, from the point of view of the y data set, this one again is an outlier. But in this chapter, outlier in the two-dimensional, for the two data set, this one is on the form. So this one is not an outlier. Because although this one is far away from here, but it's still on the form. So this is not an outlier. So this is not an outlier. But instead, this one is, if we use the method in the chapter 1, this data is here for x data set. This here, this here, this here, this here, and this one is here, 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 here. Looks like this one is not outlier, because it is in here. Right? But also for y, this is also not outlier from the definition in the chapter 1. But for this two-dimensional data set, this one is the form, and this one definitely is outside of the form. So this one is an outlier. So if a data set is an outlier, if a data is an outlier or not, it depends on how we look at this. Right? So one-dimensional data or two-dimensional data. Here we have another example. Once we know if we are given or we draw the scatter plot, we need to know how to interpret this. Here we are given a scatter plot. The x variable is the IQ score, and the y variable is the GPA. For example, for this data set, the IQ is around 85 and the GPA is around 3.2. We have all this data set plotted as in this scatter plot. If we are given this, we want to know what happened in this data set. So the first one, describe in word what this plot shows. This plot shows the GPA with respect to the IQ score for some student. The second, describe the direction, shape, and strength. Are there any outliers? So how to do this? Maybe this looks like not that the strength is not that strong, but we can still try to find the form. So it looks like the form must be straight. So it looks like will be this. We cannot put any curve or anything else. So the best guess is this is the straight. So this is the direction is linear. Sorry, the shape. The shape is linear. And once we decided the shape is linear, then the direction is easy to determine because this is positive slope. So it's the direction is positive. So it's positive, and the shape is linear. And the strength, definitely that's easy to understand. The strength is very big. So the strength is very big. Not all, not even close. Not all the points are on the form. Are there any outliers? Outliers, again, that depends how we look at this. You may see this one is outlier, and maybe this one is outlier because this form is linear, so it looks like suppose all the points must be around this, but this one is a little bit far away. Maybe this one is also outlier. This one looks like good enough. So, but anyway, if we are looking for outliers, if we are looking for 1, 2, or 3, then my best candidate will be this one, this one, and this one. So that really depends. Sometimes you may see this one is also outlier, this one is also outlier. So that depends on your application. But to be safe, we can see these 3 are outliers. Once we find these outliers, we want to know what happened to these outliers. The first one is, first guess is your data measured incorrectly. For example, you test the score, IQ score is not correct, or this is something else. But suppose if all the data are correct, and then what happened to this? So this one, look at here, the IQ score is not that low. This is almost right in the middle here. This is 103 or 104 something. So the IQ score is not an outlier around this here, but the GPA definitely is an outlier because all other GPAs are around this point, but this GPA is here. So this one, the GPA is extremely low. So we can claim maybe this student is didn't spend too much time or has something. But anyway, his GPA is not that high compared to his IQ score. How about this one? This one for the GPA score looked like here. It's not outlier because all the GPA is around 2 and maybe some like 11 here. So this is right around in the middle. So that is okay. It's not outlier in the GPA, but the IQ score here is like 70 or 70, a little bit more than 70, and all others are around 75 to 140 something. So that's definitely an outlier in the sense of IQ score. So if we want to explain what happened to this student, we may say he has a very good way to study or study very hard or something. But anyway, although the IQ for him is low and his GPA is pretty good. So that's how we explain these outliers. If we look at all this data, as we said, the strength is very weak. And sometimes we even have more data. Like this, the data set is even larger than the other one. Sometimes we have thousands or more than millions of data. It's not easy to see directly the form. So what we do is we are going to smooth the scatter plot. How to smooth the scatter plot? We take this one as an example. One way is, for example, if the data set is not that large, and we can do some simply average the y values separately for each x value. We take the example here. Suppose, see. For example, here. Right, so here. And for this x value, maybe 41 or something, and we have several y values, maybe here, maybe here, maybe here, maybe here. So where to put the fitted curve? Right? We take the value, the average of all these y values. So this, and this. So the average, okay, so maybe right at this point. So we take the average of these y values for the same x value and as the point on the fitting line. And same thing for this. So this point, this point, the average may be equals here, and all others here. So we can do for each x value, for each different x value, we average all the y values and to plot a fitted line. So that is one way. If sometimes the data set is very large, or sometimes it's very small. For example, like this. Here, for this value here, for this one, for this data set here, so here, for this x value, maybe 45, we have only one y value, which is here. How to deal with this one? We do not want to draw the line across this point, because this one will make this not smooth. Instead, we are going to use special fitting techniques to still draw the line, although not passing this one, because we cannot use average, because there's only one value. If you use average, then this value must be like this. So we can use some other techniques, use the software, and still draw the line. So this is very similar to the least square fitting we are going to discuss next chapter. But anyway, for special cases, we are going to have special softwares or to use to smooth the scatter plot. Smoothers are resistant to outliers. If you have one outlier like this, then you put one at here, then it will not affect too much of the fitting line. So that is the beauty of the scatter plot smoothers.